Okay, in this section we're going to talk about the greatest common factor of two numbers. And we have discussed the definition of a factor in previous clips. The greatest common factor, to understand the definition of this term, we simply need to know what the words greatest common and factor mean. And although that seems like kind of an obvious thing to say, a lot of times when students mess up greatest common factor, it's because they don't really understand the concept of a factor, that they don't really understand the definition of a factor. So, as a definition of greatest common factor, again, it's simply the largest number that is a factor of both of the numbers you start with. So for example, if we were asked to find the greatest common factor, abbreviated usually GCF, of 12 and 28, then we're looking for the largest number that is a factor of both 12 and 28. Okay? Now, there are a couple of methods that are employed in elementary school to compute greatest common factors. One method is a so-called brute force method that just writes down all the factors of 12, writes down all the factors of 28, and just picks out the greatest one. So we could simply write out the factors of 12, and this could be a good exercise for students just to refresh the concept of factor in their minds. And we could also write out the factors of 28. The factors of 12 are 1, 2, 3, 4, 6, and 12. The factors of 28, 1, 2, 4, 7, 14, and 28. So the first stage is just kind of running the definition greatest common factor backwards. We first start with factors. We've written out all the factors. The next thing we can do is look at common factors. Which numbers are in both lists? Well, 1 is certainly a common factor. 1 is a factor of both 12 and 28. 2 is certainly a common factor. It's a factor of both 12 and 28. And 4 is also a common factor. It's a factor of both 12 and 28. So again, now we're working our way backwards. We first started writing out all the factors. Now we identified the common factors, and the last thing we have to do is identify the greatest of the common factors. Well, that's obvious. If the common factors are 1, 2, and 4, the greatest common factor is 4. This is a technique that you see in many elementary school curricula for computing greatest common factors. However, you might notice that it's a pretty inefficient method. It's going to work perfectly for numbers like 12 and 28, numbers that don't have a lot of factors, because it's not going to take a lot of time to write out the list of factors of both numbers. But if we have larger numbers that have many more factors, this is going to be a very, very inefficient way of computing greatest common factors, because we're going to be writing out lists of factors all day long. Okay? So we can use a prime factorization method that will be a lot more efficient and will reduce a lot of the computation necessary in computing greatest common factors. So let's see how we would use a prime factorization method on a problem like the greatest common factor of 72 and 180. Now imagine if we were using our previous technique to find the GCF of 72 and 180. We would have to write out all of the divisors of 72, and we'd have to write out all of the divisors of 180, and there are a lot of them. Okay? So instead, we use the fact that the primes are the so-called building blocks of the integers, or the whole numbers in this case, and we just find prime factorizations of 72 and 80. Okay? So we can use factor trees to do this. This is good review. So 72, to find the prime factorization of 72, we just look for two numbers that multiply to 72. 8 times 9 is 72. 8 is not prime, but it can be written as 4 times 2. 2 is prime, 4 is not, but 4 can be written as 2 times 2. So 8 is 2 times 2 times 2, and 9 is not prime, but it can be written as 3 times 3. So 72 looks like it is 3 factors of 2 and 2 factors of 3. On the other hand, 180 is quite clearly 18 times 10. Neither of these are prime. We can further factor 18 as 3 times 6. 3 is prime, 6 is 2 times 3, both of which are prime. 10 can be factored as 2 times 5. So what we see is that the prime factorization of 72 is 2 times 2 times 2 times 3 times 3. And the prime factorization of 180, it looks like it is 2 powers factors of 2, 2 factors of 3, and 1 factor of 5. Okay. Now, keep in mind that prime factorizations are really the most efficient way of writing out lists of divisors of numbers. we could, if we wanted to, list every single divisor of 72 simply from the prime factorization. I'll just get us started. 2 is certainly a divisor, 3 is certainly a divisor, but 2 times 2 is a divisor, and 2 times 3 is a divisor. Basically, any combination of these factors of 72 multiplied together is a divisor of 72. So even though it doesn't look like it, we've approached these problems in slightly different ways. We really have written out all the divisors of 72 here if you really think about it, and same with 180. Okay. So we are looking, again, recall, for the greatest common factor, in this case of 72 and 180. So we can just pair up primes. It is clear that 2 is a common factor of 72 and 180 because 2 appears in both factorizations. It's also clear that, in fact, 2 factors of 2, or the number 4, is a common factor of 72 and 180 because actually 2 factors of 2 appear in each factorization. So from what we've seen so far, the number 4 is a common factor of 72 and 180. But we also see that a factor of 3 is a common factor of 72 and 180 as well. Now keep in mind, what we're looking for is the greatest common factor of 72 and 180. Now since each of these common factors are individually common factors, the greatest one is going to be the factor we obtain when we multiply all of the common factors together. And this is going to be a general procedure for computing greatest common factors. So in this case, the greatest common factor of 72 and 180 is just the product of all of the common factors found in the prime factorizations. In this case, 2 times 2 times 3, which is 12. This process can be used in general to compute greatest common factors, and it's far more efficient than our earlier technique of just writing out all the divisors. So again, just to recap, to find greatest common factors, we first find prime factorizations, then we match up all of the primes that are common in each factorization, and if we multiply all those together, we're going to get the greatest common factor of the numbers we start with. This is a technique that can easily be used in elementary school because it is certainly grade appropriate. All we need to know are prime factorizations and the definition of factor. It turns out that there's another technique that can be grade appropriate as well called Euclid's algorithm. It is not often taught in elementary school. For that reason, I will include a discussion of Euclid's algorithm as a PowerPoint that accompanies this